Okay, recording has started, so good morning everyone. Welcome back to Math 115. So today we are going to discuss sections really just section 4.2 really. And we're going to go nice and slow and talk over the trigonometric functions, which are going to be basically the basis of what we do in this class for the next really long time. So just like how when we started this class, if you didn't know how to do, say, basic algebra, you would be at a major disadvantage. For the rest of this class, if you don't have a basic idea of what we do today, you're going to be in trouble for what we do for the rest of the class. So we're going to go nice and slow. We're going to do lots of examples, and then we're going to not jump into the harder material until we feel like we're happy with the basic trigonometric functions, okay? So regarding your homework, you have two homeworks which are due today. Or actually, I guess it's three homeworks, right? Because there's a 3.3 A and B. And then there's 3.4 as well due today. And then homework 4.1 is going to be due on Friday. Okay, so we finished 4.1 already. That's due on Friday. I assigned a homework 4.2, which is going to be due on Monday. 4.2 due Monday. Okay, so your next assessment is going to be in class tomorrow. It's quiz 5, and it covers sections 3.2 to 3.4. So we studied those during office hours yesterday. But if you didn't have a chance to come to office hours yesterday, you have another chance today because my office hours are moved this week. I moved them before the quiz, so they're going to be today from 9:30 right after class. I'm going to walk right over to my office and go from 9:30 to 11. So that is going to be when my other office hours are. So no office hours on Thursday this week is the long short of that, and we will be in my office today. If you can't make it to my office hours, then always go to the tutoring center. They can help you there almost as well as I can help you. Pretty much as well. All right. Are there any administrative questions before we start in on content for today? Yeah.
Did you record office hours or something?
I was not able to record office hours yesterday because we got kicked out of our favorite room. So we had to go over to the tutoring center. So I will record office hours whenever it's possible, but generally speaking, it's not necessarily going to be possible. Does that make sense? Okay, so I'll try if I can. All right. Any other questions? All right. I just want to remind everyone, by the way, that the quiz questions come directly from the homework. So if you look at all of these three homework assignments, okay, you can put a sticky note on your desk and write down like 3.2, number 1, 3.2, number 2, ... And you can put a check mark next to the ones that you feel prepared for if they were to show up on the exam, right? So what I would do if I were studying for these quizzes or exams is I would go through these problems and I would make a list. And until I had a check mark next to every single problem, I would not say like, oh, I'm ready. I would say, once I have a check mark next to every single problem, then I'm happy. You don't necessarily have to do every problem, but you need to be able to look at the problem and say, yes, I know how to do that. And you need to be confident enough in that answer that, you know, the yes should mean I definitely would ace this if it showed up on a quiz, right? Then if you do that, then there's no chance that you're gonna get a bad grade on the quiz or on the exam. All right. So that's about the quiz. So let's get back into it with trigonometric functions. So last time we had to finish the previous section. So we learned about arc length, okay, the relationship between arc length on the unit circle or on any circle of radius r, and if we have an inscribed angle with angle theta, then the arc length will be theta times r, as long as, what is true? We must have theta to be measured in radians. If you put it in degrees and times the radius, you're going to get a number, but it's not going to be a meaningful number. It's not going to be the arc length. It's not going to be anything. Okay, so we did a partner practice, and then we moved on to 4.2, where we reviewed some basic concepts such as the unit circle, okay, and also special right triangles. So basically 3 special right triangles we need to be concerned about. There's the 45, 45, 90. There's the 30, 60, 90. We need to be able to understand how to find the side lengths of some of the sides if we know maybe one of the sides, okay? Basically, that's what we need to do with these two. And we also learned about Pythagorean triples and 3, 4, 5 triangles, 5, 12, 13 triangles, etc. So this is just numbers that are related by the Pythagorean theorem, which is, of course, a squared plus b squared equals c squared, tells us how to get the length of the hypotenuse if we know the length of the sides. Or really, it tells us how to find the length of one of the sides if we know the other two, right? If we know the other two sides, then we can figure out the length of the missing side. All right, so then we had another partner practice, okay, which involved the Pythagorean theorem, right? What did we do? We wanted to find the points with height 3/5. So we here's one with height 3/5, but of course there's another one over here, right? And then we made these triangles, and we noticed that both of these triangles, okay, the y value, meaning this height here, is 3/5, of course, right? This is 3/5. And the x value is to be found. The final piece of the puzzle was that we actually know what the hypotenuse is. We always know what the hypotenuse is. It's always 1, because this segment from here to here goes from the inside of the circle to the outside of the circle. That means its length should be the radius, and the radius of the unit circle is 1. So once we had that, we were able to just plug into the Pythagorean theorem. When we ended up taking a square root, of course, we get a plus or minus. In this case, this represents the fact that we have a point with height 3/5 on the right side and a point with height 3/5 on the left side of the unit circle. Okay, so you could also visualize this as like, at what 2 points will the unit circle cross the line y equals 3/5, right? It will intersect at exactly 2 points, these two, right? Okay, so if you cut a circle like this, then this segment here is called a chord. Okay. Any questions about what we talked about last time before we jump into something new?
Are we gonna need to know the whole unit circle for the next analysis?
Are you going to need to know what?
Like the whole unit, like I don't know.
Like the equation of the unit circle,
The
or
whole, like all the measurements.
the trigonometric values at different points on the unit circle? Is that what you're talking about?
3 pi over 2, 2 pi over 3 pi. You know what I'm saying?
And like the
Like how I learned this in high school, so maybe I'm being stupid, but
No, I think I know what you're talking about. What you're saying is we're going to make a unit circle, and then we're going to do something like this. We're going to do like, one of these, one of these, one of these, and one of these, and something like this. And then we're going to label all of these like, okay, this one's 0, this one's like pi over 6, blah, blah, blah. And also, we're going to take the points on here, which we're going to say, well, what are the coordinates of these points, right? And what is the coordinate of this point, and this point, and this point? Is that what you're talking about?
yeah.
Yeah, we're going to get there.
Okay.
We're going to get there. I don't know if we'll finish that by the time we have the next quiz or not. Any other questions? Okay. So now let's talk about a really interesting concept, which I've actually never seen this presented this way. I think it's a really kind of a beautiful way of putting this. So what is going on here? Well, what we are going to say is, well, we can plug into a trigonometric function any angle, such as this angle, or we could do like even so much of an angle as to be like this, right? This would be a pretty crazy angle, right? But even more so than that, we can go around the unit circle however many times we want, okay? We could go like around 3 times and then end up here, right? And then what would it be? It would also have a point on the outside of this circle, right? Which we could use to find the trigonometric value from the function, right? So the way that we visualize this in terms of the inputs of the trigonometric functions, which the inputs of the trigonometric functions will be any angle. But we know that a lot of angles are actually coterminal to one another, okay? For example, the angle pi over 4 is, so this angle is coterminal to the angle 2 pi plus pi over 4, right? That would be a coterminal angle. So they're going to correspond to the same point on the outer edge of the unit circle, and therefore their trigonometric, the value of the trigonometric functions will be the same for each of these, right? So the way we can view this is in the following way. We say, well, let's just put an axis, okay? Let's put an axis on the side of this circle, okay? And then what are we going to do? This axis basically has, measurements of length upon it, right? But if you imagine that this axis was made of string, right? Made of string, then what we could do is we could wrap it around the unit circle, right? And then what would be true, okay? So here we have 1/2, so 1/2, it gets bent onto the unit circle, right? So the height of this point right here is not quite 1/2 because it got bent a little bit. It should be a little less than 1/2. If it's perfectly straight, we make it all the way to 1/2 height, but we're not going perfectly straight. And then, 1 gets over to here, right? And then how long is the piece of string which wraps all the way around the unit circle? Well, if I took a piece of string and wrapped it all the way around the unit circle, that piece of string would need to be 2 pi units long, because this is the unit circle. Its circumference is 2 times pi times the radius, which is 1. So 2 pi is the length of the piece of string which we could wrap all the way around. But what could I do next? I could, if I still had a bunch of string left over, what would I do with it? Well, I can again continue to wrap it. Okay, so I go all the way around wrapping my string, and then I just keep wrapping my string over and over and over again, right? And then what I want to ask, is, well, if I had a piece of string which was 7 pi units long, it would start here as usual. It would go all the way around to here. Now I've used up 2 pi. How much further do I need to go in order to make it to 7 pi? I need to go an additional 5 pi, which means, well, now I'm at 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. So 7 pi looks like an angle, okay, which points directly to the left, okay? So this is a really interesting way of thinking about radians, right? Because here we have just measurements, right, of length. But when we wrap those measurements of length around the unit circle, then hey presto, suddenly these represent radians. These can represent radians because, remember, radians were the angle measurement such that, okay, here's 1 radian. Here's 1 radian. 1 radian is the angle measurement needed in order to produce an arc length of 1. So if you wrap a string with length 1 around this unit circle, okay, then the input of the trigonometric functions, which will be this angle, will be the same as the length on this axis, which we have wrapped around the unit circle. Okay, so this is a bit of an abstract concept, but I think it's really instructive. We'll come back to this later. Okay, so it's time to learn about trig functions. Okay, it's time to learn about trig functions. So I don't want anyone to get too scared. We're going to go really, really slow. So what do we say? We let t is going to be the letter we use for the input for now. Sometimes we'll use x or theta or something like that. But for now, we're going to use t as the input. And the input of a trigonometric function should be a real number. Okay, should be a real number. We'll talk more about the domain of these functions later on. But if t is a real number, okay, we allow this real number to represent an angle inside the unit circle. Okay? So t is going to measure this angle here. This measure here is This angle here is measured by t, which correspondingly means that the arc length will be t units. Okay, so this looks like about 1 radian or like 60 degrees or something like that, right? Okay. Then, if we put such an angle inside of the unit circle, the terminal side of this angle, which the terminal side is this side of the angle, the terminal side of this angle will point at a point which is on the unit circle. Okay? So I'm not saying anything crazy here. I just say, look, if I'm initially facing towards you and I turn a certain amount, there's a point on the wall which I am facing towards, right? Nothing crazy. There is a point at the wall which I am currently aligned towards, right? So if we turn a certain amount here and we look in this direction, we can see, aha, if I were to walk straight ahead, I would touch this point on the unit circle. Okay, so the initial side of our angle always goes on the positive x-axis, and then we just turn until we have turned however many radians we have, or however many degrees we have. And then we shoot out a ray, and this ray will cross the unit circle at a point, and this point lives in the coordinate plane, right? It has a height and a width. Yes, it has a height and a width. Okay, so this point lives in the coordinate plane. And what we are going to try to describe is, well, if we turn t radians and we look at the point which we're pointing at, we want to ask ourselves, what are the coordinates of that point? What are the coordinates of that point? Okay, so this is what the trigonometric functions were invented to do. Okay, so this point has an x value and it has a y value. Okay, so here's an example. This would be the x value, right? Whatever this length is. And then what would the y value be? It would be whatever this length is. We could do another example. What if I were to use this angle? If I were to use this angle, then where's the point? It's right here. This is the point, and its x-coordinate is this length, and its y-coordinate is this length, right? So we could draw a little triangle here. Okay, we could draw a little triangle here. And guess what? We're going to know what the side lengths of the triangle are, because what's this one? It's 1. It's always 1, right? And then we're going to use 30, 60, 90 triangles or 45, 45, 90 triangles to figure out what the other two legs are. Okay, so time to define the trigonometric functions. If you put an angle t inside the unit circle, it points at a point, and that point has an x-coordinate and a y-coordinate. We define sine of t, okay, is defined to be the y-coordinate of the point on the unit circle, such that if I put t inside of the unit circle, it points at a point with height y. Okay? So I want to be clear here that the definition is we are defining this to be this. This thing, the y value exists as long as we put t inside. There is a y value. We call that y value sine t. Sine t is the name that we give for this y value. So I'm not saying that the y value is going to be given by sine t. I'm saying the other way around. Sine t is going to be given by the y value. So I put the angle t inside of the unit circle, like so. And then I ask myself, what is the y value of that point which I am pointing towards? And whatever that y value is, that is what I call sine t. Any questions so far? Yeah.
Can you zoom out a little bit?
Yeah, sorry. Any other questions so far? Okay, so what does sine go with? Sine goes with the height. Sine goes with the height. Okay, so it's always going to be given by whatever is the height of the point. So, for example, what if t was a 90-degree angle? Then here's my point up here. What are the coordinates of this point? 0, 1, right? Yeah, 0, 1. So what is sine of 90 degrees? 1, right? It should be the height of the point on the unit circle, which is pointed at when I put a 90-degree angle inside of the unit circle. We okay so far? All right, I know for some of you that this might be painfully slow, but we want to go slow right now because we want to be really careful and get a good grasp of these early on. Okay, so now let's talk about the other trigonometric functions. Well, the cosine of the angle t, cosine of t, is going to be given by what? The x value of this point. So the height of the point is the sine. The width of the point, okay, or the x value, is cosine. Okay, so the inputs of the trigonometric function are angles. The outputs of the trigonometric function are the x value, which is pointed at when you put that angle inside of the unit circle and you trace this all the way along to the point. Okay, so that's cosine. So sine and cosine are your most basic ones. In fact, all of the other trigonometric functions are really a function of these two. So sine and cosine are the most important ones, and the next 4 are just an extension of that. Because see here, what is the tangent? Okay, tangent of the angle t. We put the angle t inside the unit circle. We point at this point. It has coordinates x, y, and what do? We take the y coordinate and we divide it by the x coordinate. So how is that related to sine and cosine? Well, sine is what I get when I do the y coordinate, right? And cosine is the x coordinate. So what is tangent in terms of sine and cosine? Yeah, sine of t. If you take sine of t and you divide it by cosine of t, remember, sine of t is y. So this is y divided by x. Y divided by x. Okay, so the next 3 are less commonly used trigonometric functions. Okay, we call them cosecant, secant, and cotangent. Okay, and I'm going to tell you now that there's something really, really, really annoying about the first 2, cosecant and secant. Has anybody taken a little bit of trig before and can tell me why cosecant and secant are so poorly named?
Cosecant is the inverse of sine and secant is the inverse of cosine.
Exactly. Madeline's got it exactly right. Cosecant is 1 over y. What is y? Y is sine. So cosecant could be rewritten as 1 over sine of t, and secant can be written as 1 over cosine of t. Okay, and the last one is 1 over tangent of t. So that's super annoying because we think, oh, well, cosecant should go with cosine, shouldn't it? But they don't. They don't, sadly. But as long as you remember that it's really messed up, you'll remember which one goes with which. Okay? So just remember that the world is not as it should be. And then you'll be led to the correct answer. All right. So these are the trigonometric functions. What do? We put the angle inside of the unit circle with the initial side pointing to the right. We measure however much that angle is, and then we have the terminal side. The terminal side points at a point on the outside of the unit circle. That point has coordinates in the coordinate plane. The y-coordinate is sine. The x-coordinate is cosine. The ratio of the y-coordinate to the x-coordinate is tangent. And then the reciprocals of sine, cosine, and tangent, the reciprocals become 1 over y, 1 over x, and x over y, and we call those functions cosecant, secant, and cotangent. And you'll notice I put this qualifier out here for each of these, right? For each of these where we have something in the denominator, of course we don't want the denominator to ever be 0. So we should always keep track of, well, this will be what this function is, provided that we can actually do the division of y divided by x. If y is 1 and x is 0, we can't do it, right? So in that case, tangent would not be defined. Okay, let's pause for a second. How are we feeling so far? Let's have some thumbs. Raise them high. Thumbs up if we feel like I'm ready to do some examples. I feel well equipped. And thumbs down if this is still confusing. Can we go through one more time? Thumbs to the side if you're somewhere in the middle. Okay, I'm seeing mostly middle and up. So I think we're gonna move on because as much as I can go back through this over and over again, I think it will be instructive and helpful and clear things up to see a bunch of examples. So we're going to just do a ton of examples today. That's all I have planned. We're just going to do examples on examples on examples. Okay? Okay, so I'm going to move this off of the screen. Maybe we'll come back up here later. But what I want to do is rely upon my memory to try to compute these items, right? Okay. So, first one up is cosine of pi over 4. In fact, why don't I move the other stuff down. Let's start with this one. Find cosine of pi over 4. The first step, every single time, no matter what, when we're doing trig, is if you're not drawing a circle right away, I don't know, you're not right. Okay, my point is you should draw a circle right away, every single time, anytime you're doing anything related with trig. Okay, so now what do? We need to inscribe the angle pi over 4. Okay? How can I know what the angle pi over 4 looks like? That's not very familiar to me. Pi over 4 looks weird. Yeah, Andrew? Yeah, you can convert it to degrees, right? And then maybe it'll be a little bit more friendly. What would happen if I did that? Well, pi over 4, how do I convert to degrees? Multiply by what? 180 divided by pi. Good. The pi's cancel. We knew that was going to happen because we're going to degrees, right? Okay, and then what do we have? We have 180 over 4, which is 45 degrees. So what does a 45-degree angle look like? Can someone describe that for me qualitatively? Yeah, half of a 90-degree angle, right? So what does it? We know, everyone knows, everybody knows that this is a 90-degree angle. So what would half of that look like? Well, I'm just going to draw something like this. That would be half of a 90-degree angle. Okay, so, excuse me. Thank you. So here's pi over 4, okay? My goal for you all is to, by the time, like a few days from now, you'll look at pi over 4 and you'll say, aha, I know that goes right here. Or I'll say 7 pi over 4, and you'll say, oh, well, that's almost 8 pi over 4, which would be 2 pi, so I know 7 pi over 4 would be like right here, right? So my goal for you is to be able to look at radians when they're written in terms of pi and be able to see exactly what that angle should look like without having to convert to degrees. But for now, if you need to use the crutch of converting to degrees, there's no problem with that. Just know that it introduces an extra step for you to do, right? So A, it's more work, and B, it's a chance for you to make a mistake in your calculation. Okay, so where do I go from here? I inscribed the angle inside of the unit circle, and what is going to be relevant for finding this number? What now is going to be relevant for finding this number? Gavin? Very good. The coordinates of the point on the unit circle. Which point? This one, 1, or 2? Which point matters? The point number 2 matters, right? It's the point which the terminal side is pointing at. And we don't know the coordinates of this point, do we? We don't know the coordinates of this point. Well, not yet anyways. But once we do know them, whatever they are, this one will be x and this one will be y. And cosine of pi over 4 will be equal to which one of them, x or y? I'm hearing both, so we should go back into our notes and check. Well, it says cosine t is going to be the x value of the point, so I'm going to go back, flip through my notes until I find this page and I see, aha, cosine of t should be x. So that's what I would do on my homework. I'd look back at my notes. So it's the x value of this point. Now, open-ended question for the class. How do I figure out what that coordinate is? How do I figure out what that coordinate is? Well, the length here is 1. That's something we can fill in. We can fill that in. What else can we fill in? We know that this angle is pi over 4. This angle is pi over 4. What else did we learn when we were just starting this section? We reviewed some stuff. What did we review? We reviewed the unit circle. Okay, so we've already got the unit circle drawn. What else did we review? Special right triangles, right? Special right triangles. What was great about special right triangles? If I know the length of one side of a special right triangle, I can figure out the lengths of all of the other sides. So how can I use a triangle? I don't see any triangles here. We can make one. So we form a triangle. By dropping a line from the point to the x-axis as shown. We drop a line like shown, and now suddenly we have a triangle. Okay, suddenly we have a triangle. So one thing I want to point out, by the way, is it is important that we always drop this line in a vertical fashion. We draw a vertical line, so we always draw a vertical line segment to complete the triangle. Okay, so what I do not want to do is something like this. Okay, it's confusing because Well, this would give us a little triangle here, right? It would give us this triangle. But we always want to make our triangle like so. Okay, we always want to make it like so. Okay, we drop a line to the x-axis, and then what is this? This is a 90-degree angle. So what is this angle? It's also 45, right? Or pi over 4. So it's a pi over 4, pi over 4, pi over 2 triangle, or 45, 45, 90 triangle. Okay, so let's go back to our notes to figure out how is it that I find the other side of a 45, 45, 90 triangle when I know the hypotenuse. Well, I'm just going to go straight back to my notes. Here it is. It says, well, if you know one of the short legs, you can find out what the long leg is by taking that short leg and multiplying times the square root of 2. And what was it that we needed to do to go the other way? If we know the long leg, how do we figure out the short leg? We divide by the square root of 2. So that's what we're going to do. So we know the long leg is 1. So what should the x and y coordinates be? They're going to be the same, right? The x and y coordinates are going to be the same. How do I get them? Divide what by the square root of 2? 1. Divided by the square root of 2. Okay, but I've got a square root in the denominator. What do I have to do? Multiply by square root of 2 on the top and bottom, right? If I do that, then I get on top square root 2 and on bottom 2. And then again, this is a 45, 45, 90 triangle. What relationship holds between the two short legs? They're the same. So this one again is square root 2 over 2. So cosine, I want to use pink, I think. Cosine is going to be the x-coordinate of this point. So cosine of pi over 4 is equal to what? Square root 2 over 2. Yeah, if you do square root 2 divided by 2, you'll get that number. Because square root 2 is like 1.4 something. So divide that number by 2, you'd get 0.7 something, right? Yeah, so square root 2 over 2 is the clean way of writing it, so that we don't have to write out all those decimals, right? Because if you wanted to write it exactly, you'd have to write out an infinite number of decimals, which who's got time for that? Literally no one. All right. So let me recap and then ask if there are questions. So in order to find cosine of pi over 4, what did we do? We drew a unit circle. The first step of every single trig problem is always to draw a unit circle. In this case, the second step was to draw the inscribed angle, which was pi over 4. It's a little bit tricky if you're not used to using radians to know what does pi over 4 look like. So what's a trick we can use to fix that? We can convert to degrees. We can always convert to degrees. You multiply by 180 over pi. Okay, so then finally we had an angle in here. And then we were confused because we were like, well, there's a point here, but I don't know how to figure out what the coordinates of that point are. Well, the special way in which we overcame that was this is almost a triangle. It's almost a triangle. The only thing I need to do to make it a triangle is to draw in an extra segment. And the extra segment which I draw in will always be a vertical line segment, okay? The line segment should connect the point on the circle to the x-axis. Okay, once we had that, we were able to identify that this triangle was a 45, 45, 90 triangle. So we can figure out the side lengths as long as we know at least one of the side lengths. But here's the catch of the trigonometric problems. We always know one of the side lengths. Which side length is that? The hypotenuse. We always know the length of the hypotenuse because it travels from the center of the circle to the outside of the circle. That means it should have the length which is equal to the radius. So the radius is 1, so that's what goes here. Okay, after we figured out that that was 1, we just used the theory of 45, 45, 90 triangles to identify, well, we should divide by the square root of 2 in order to get the length of the short sides. And the two short sides have the same length. We simplified a little bit and got square root 2 over 2. Once we know the coordinates of this point, we can figure out what cosine pi over 4 is, and we can figure out what all the other trigonometric functions are. Let's go ahead and do those now. What would sine of pi over 4 be? Square root 2 over 2, again, right? Because I take the y coordinate. That's how I get the sine of this angle. It's the y coordinate of the point on the unit circle which this angle points towards. How about tangent of pi over 4? What would I get when I do that? I'm gonna get 1. Why? Because what I take is the y value, which is square root 2 over 2, and I divide it by the x value, which is square root 2 over 2. If I divide something by itself, I just get 1. Okay? How about cosecant of pi over 4? Which one does cosecant go with? Cosecant is 1 over what? 1 over sine. Because cosecant, we wish it went with cosine, but the world is not as it should be. Instead, cosecant goes with sine. So it's 1 over sine of pi over 4, which in this case would be what? 1 over square root of 2 over 2. In other words, it would be 2 over the square root of 2, which would be just the square root of 2. Okay, why don't I simplify it out? Square root 2 over 2, but we have, 2 over the square root of 2, but we have a square root in the denominator. We take care of that by multiplying by the square root of 2 on top and bottom, which gives us 2 square root 2 on the top, and what on the bottom? Square root of 2, or just 2. And then we cancel these 2's, and we get what? Just the square root of 2. Okay? Why is that? That's because square root of 2 over 2, initially, what did we have? We had 1 over the square root of 2, but we rationalized the denominator to get it to look like this. So if you flip this, okay, flip it, then you get the square root of 2 over 1, which is cosecant. All right, how about secant of pi over 4? What's that one going to be? It's going to be 1 over cosine of pi over 4, which is again going to be what? It's going to be just the square root of 2, yes? And how about cotangent of pi over 4, the last one? How do I get the cotangent? Well, I can do it in 2 ways. I can do x over y, or if I already know what tangent is, then I can do 1 over tangent. So I already know tangent is 1. Tangent is 1, so I'm going to do 1 divided by tangent, which is 1 over 1, which is 1. Okay, that's because if you divide the y value by the x value, that's the same as dividing the x value by the y value, because these two numbers are the same. Okay, so we have found the value of all 6 trigonometric functions for pi over 4 now. So let's pause for a second because we should take some time now to address anything that's not quite clear about this. So are there any parts that either you have a question on or you're not sure how to phrase your question on it, but you're still confused? Yeah, Gavin?
It's not really like a big question, but just like, are we ever gonna need that point, like the point on the circle itself, like actually find anything, or are we just gonna use that to like create the triangle?
Well, we're gonna talk a lot about this going forward, so I won't spoil anything. But yes, we're gonna be talking all about this point and the trigonometric functions for quite a while now. All right, that's it for today. What's up?
Where's office hours?
Oh yeah, I have office hours starting now. I'm gonna walk over to my office in Lacan.